Affine Body Dynamics enables penetration-free stiff material simulation, but scaling remains difficult. Distributed simulation offers an effective path to scaling, but it comes with several challenges. Our contributions are threefold. First, our system enables multi-device ABD simulation while preserving non-penetration. Second, we introduce a mass-aware adaptive consensus mechanism that significantly accelerates ADMM convergence. Third, our framework delivers efficient parallel speedups in distributed settings, achieving near-linear scaling in our experiments. We simulate a Pokemon scenario with over 5,000 ABD bodies. Objects fall through a narrow funnel and interact with two rotating perforated plates inside a container. The simulation handles tens of millions of collision candidates and achieves a 1.7 times speedup using two workers. Here we also provide a zoomed-in view of the Pokemon scenario for a closer look to highlight the congestion and squeezing at the funnel. We evaluate our load balancing strategy in a 4-worker setup and observe a 35% speedup over static partitioning. In weak scaling, we grow the problem to keep per worker work constant, aiming for near constant runtime. Here we show the result of weak scaling with 8 workers and the runtime remain constant. In strong scaling, we keep the problem fixed, aiming for near 1/n runtime with n workers. The video shows the result of n equals 8, illustrating near-linear speedup as we scale to multiple workers. With our mass-aware adaptive consensus strategy, our system exhibits stronger convergence than other comparable methods. A large-scale dropping simulation with over 27,000 ABD bodies is shown. The scene contains 16 million triangles and reaches up to 164 million collision candidates and 222,000 active contacts. The simulation runs efficiently across 6 workers, achieving a 5.2 times speedup over single-worker execution. In this experiment, a rotating drum agitates 2,323 complex, non-convex ABD bodies with 16.1 million triangles, generating up to 53.6 million collision candidates and achieving a 1.5 times speedup on 2 workers. We further present an industrial parts simulation with over 7,000 interacting ABD bodies. The scene contains 13 million triangles and generates 452 million collision candidates and 338,000 active contacts. Such dense interactions are handled efficiently across 4 workers, exceeding the memory capacity of a single GPU setup. The scalability of the distributed framework is evaluated on fluid simulation and solid-fluid interaction. The system scales to 1 million fluid particles together with 220,000 triangles across 4 workers, demonstrating that the approach extends beyond ABD bodies to large-scale coupled simulations. We evaluate load balancing in a 4-worker setup and observe a 35% speedup over static partitioning. Thanks for watching. More details can be found in the paper.